Right, so question 3 is 8 quick torsion questions. So let's give them a go. Write out the engineer's torsion formula. Make sure you use all of these terms. So you need the applied torque, the polar second moment of area, the radius, where you're going to measure your shear stress, the shear stress, which is at the radius position R, G, which is the modulus of rigidity, or some people call it the shear modulus, theta, which is the angle of twist, which is measured in radians, and the length of the shaft. And of course, there's no need to put your hand up here, so let's cross that out. So write out what the equation is. See if you can do it without using your formula booklet. And when you're ready, press play and we'll move on. So you should have your torque divided by your polar second moment of area. That's your first column. Your next column is your shear stress divided by the position where you're measuring your shear stress. And your last column is the shear modulus times by the amount of twist that you got divided by the length of the shaft. So that's what you should have. We've got a solid circular shaft. It has a diameter d and it's subject to a torque of 1,000 Newton meters. If the maximum permissible shear stress in the shaft is limited to 30 megapascals, determine the minimum value that you're going to have for your diameter. So you want to use your torsion equation. Go back to that, have a look at it, see where you can start plugging your numbers in and where you can work out your various terms here. You're going to think about where maximum shear stress is going to be, and need to think about that, and should be able to solve it. When you're ready and got an answer, press play. So what we need for this is obviously we need to start off with our torsion equation. And the two columns that are going to be of interest here is obviously we've got something to do with torque and we've got something to do with shear stress. So we've got those two variables. And here we can see that there's this polar second moment of area is going to be dependent upon the diameter. It's going to be a lookup value that we lookup formula that we use for that. And where is the maximum shear stress going to be? Well, it's going to be on the outer side of the shear of your shaft, so therefore it's going to be at half d. So these two terms are both dependent on d. So what I did was took your J formula, substitute it in, and the R, replace that with d over 2. Notice that we're looking for d here, so it's best to work in terms of d. So a bit of rearranging there. 32 is divide by ends up as 32 on top. Again here, the half, or the 1 over 2 divide by ends up as a 2 on top. So let's rearrange this. 2 goes into the 32, so we end up with 16. Anything else we can simplify? Well, we've got d to the power 4 here, and we've got d here, so d to the power 4 can drop down to d to the power 3. We want to put this into our calculator, so we want to put 16 times by the 1,000 divided by pi, and the maximum stress that we're allowed is the 30 megapascals, so we want to put in the 30 megapascals there. So there we go, and we should get a solution of 55.4 millimeters. What is the applied external torque on my orange shaft here? So I've put in a load here, or a force going off it at this angle away from the vertical. So what's the torque going to be? If you've got an idea, well, please pause the video, work out an answer, and when you're ready, press play. So in this case, we're going to do torque is force times distance, and they need to be perpendicular. So we need to decide which ones to make perpendicular. The most logical thing is to make our force, which is going off in this direction, point off in this direction here. So we want to just take all that force and take the fraction of that force there and see what fraction of it is pointing directly downwards. So to do that, we need to take out A to multiply it by cos 60. I'm going to resolve it to this line here. Yeah. So we're going to have that, and then we got the 1.2, which is representing the distance. So you should have ended up with an answer of 4.8. Find the polar second moment of area for this bronze shaft below. It's got an outer diameter of 24 millimeters and a thickness, so that's the thickness there, of 6 millimeters. Right, so look up the formula that you're going to need in your formula booklet, and when you're ready, work out an answer, press play, see the answer. So here we can use the avoid method to find the polar second moment of area. So we're going to have the outer diameter, d to the power 4, take away the inner diameter, d to the power 4, put them all in brackets so we can sort of make the pi common, factorize the pi, and the 32. So here I've got 24, and I've got to say to myself, all right, so if I've got 24 outer, so that's going to be 24. I need to find the inner diameter, but I've been told the thickness, not what the inner diameter is. So that would be 24, sorry, 12 there. That would be 24 take away, well, the thickness is 6, so 6, it's 2 thicknesses, obviously, one here, 6 times 2, so that's 12, so 24 take away 12 is 12, so that's where we get the 12 from. The bronze shaft below has an outer diameter of 24, same as before, so we might want to use this number here. So we've got, what's that, 30.5 times 10 to the 3 millimeters to the power 4. So let's write that down. That might come in handy. What was that again? 30.5 times 10 to the 3, and that's in millimeters to the power 4. Okay. Right. So what is the shear on the inner surface here? So we'll use the first two columns of our torsion equation. We want to rearrange these to find out what the shear is going to be at this point here. Pause the video, try and work out the numbers in your calculator, and when you're ready, press play. Well, hopefully you chose 72 megapascals. Let's have a look at the solution. So for this particular case, what I did to solve it was say, well, if you think about this term here, we're applying a constant torque, and the cross-sectional area of this particular shaft isn't going to change. So I didn't actually use the J value. So what I said then was that if the outer shear is going to be found by this amount here, this 144, all I need to do now is scale down what the shear is going to be at this point here by the R term. Okay, so I didn't actually needed the J or the oh yeah, because I misled you there. Sorry. So we didn't need the torque. We didn't have the torque, did we? So the point to solving this question was the fact that this is constant. Okay, so hopefully my misdirection, you could still solve it. Right, so that the torque will be constant, the cross-section will be constant, and what will the shear be? Well, it will be uh, um, uh, relative to the position R. So we've gone from 12 millimeters and we're dropping to this position here. So that will be what would that be? 12, take away 6, that would be 6 millimeters. So we are basically going to make the inner position will be 6 millimeters. So that means that all we want to do is drop our shear by a half. So it's going to be half of that original value. Okay, so that was a bit more involved than I actually initially thought, because I initially didn't really read the question properly and didn't realize that wasn't talking the question. So it required a little bit of thinking there. If for a certain shaft its length is double, so its length is double, we're going to double that. And the torque halves, so this one halves. And the angle of twist will do what? What will the angle of twist do? Will it also halve? Will it double? Will it stay the same? Okay. Hopefully you could see the answer straight away would be that it stays the same, because if this is going to go up twice, that's going to get twice as big. This is going to get sorry, no, the torque halves, isn't it? Torque halves and the length gets twice as big. All the way around. So that gets twice as big. When we bring the 2 up onto that side, the half and the 2 will cancel. So therefore, the angle of twist will stay the same, because we're going to assume that the shaft material has obviously stayed the same. What is the polar second moment of area of a hollow shaft? For a shaft experience a maximum shear of 10 megapascals, so we've got that value there. It's got a torque of 9 Newton meters. Okay. It's got a diameter of 30. So, well, we're looking for maximum shear, so we know that the R is going to be half of that. So we know what the R is. So we want to rearrange this this term here to find what J is going to be. So have a go at that. When you think you've got an answer, press play. And hopefully you got the solution, which is the first one, A. So let's have a look at that. So we start off with the torsion equation. We know that R is equal to D divided by 2. We'll rearrange this to find what we're looking for. We're looking for the polar second moment of area. So we can just substitute in our values now. So we know the outer diameter, we know the amount of torque, 9, and we know the maximum shear stress we can have is 10 megapascals, so 10 megapascals there. So J, put those numbers in, will give me this solution. Okay, so that's my 8 little torsion questions. Hope you enjoyed them.